Hey everyone, my name is David Talby. I'm from Johnson Labs. Look, it writes what I speak. Cool. Okay, this is a session about helping you build large-scale text processing pipeline, open source. So we'll talk a bit about the Spark NLP library, kind of where it is today, what are people still doing with it, and then we'll talk about 3 use cases, embedding calculations, LLM inference and scale, and building end-to-end RAG pipelines. So the Spark NLP library started way back when, 7 years ago, as really the NLP library for Apache Spark, and got built into, just recently crossed 100 million downloads. So it's a very popular library for large-scale deployment of test processing, mostly for really the larger companies, so Google, Amazon, large financials, large healthcare and insurance use the library. So it's designed less for, I would say even less for ease of use, more really for the large enterprise deployments. One thing that would be interesting to know is in the last year, we've seen a 60% growth in downloads. So with the era of the LLM, actually there have been 2 use cases that we'll talk about today that have been really useful. Same thing as what the library have done before, for people who move beyond the POC stage and the playing stage and kind of say, now I need to do this in production. And now I care about latency, and I care about scalability, and I care about cost. And being able to both load RAG LLM datasets as well as really just use LLMs for inference and scale is something that's been happening more and more. So the Spark NLP is everything I'll show you today. It's open source. It's Apache 2.0 licenses, right? So it's all free and open source. There's a lot of documentation, hundreds of notebooks, a community there. There's the library itself, which most people would access through Python. So it's its own code base, but also there's a collection of more than 40,000 models. So the Spark NLP ecosystem basically has its own model hub. And what we do, there are some things we build on our own, a lot of things we import from others, but the goal is to make it a curated model hub. Okay, so basically if you want to put your own model somewhere, you can just please put it on Hugging Face. We pick things from TensorFlow Hub and Hugging Face and others, that are not duplicative, that are better than what's there, that pass our security checks, all of that, and we put them here. So this is helpful to you if you're looking for something that's kind of really intended for production use, has been tested, right? Does not have a lot of the kind of the hobby stuff, the duplicative stuff, the experimental stuff. Spark NLP is designed for Apache Spark, but you don't have to use it on Spark or on a cluster. So there are 12 supported platforms. Of course, most people just run it on their laptop. You can run it within a Docker container or on Kubernetes. You can run it on any of the clouds. Of course, you can run it on Databricks. It's highly optimized for that. You can run it on anything that runs Spark, like Amazon EMR, Azure, Google have their own managed offerings. So you can scale it then, or really you can just do it as a single machine. There are also lots of integrations, like MLflow has a Johnson Labs flavor now, right? So you can manage models, run experiments, right? Manage tuning and all of that, same with comment, and also specific integrations with Intel and NVIDIA. The easiest way to use the library is really with one-liners. So people install Johnson Labs, you import NLP, and what you do, you load the model. So here the example is you load the name entity recognition model. You tell it what to predict. So you can do it super simple as one string, but you can give it a full data frame, and it does the whole thing, or you can even give it a Spark data frame. So if you want to do it on 1 petabyte of text at the time, you can just, it's still a one-liner, and it will do it, you will do it at scale. So there are several thousand things that you can ask it to load. These are the simple things. So you can do spell checking, sentiment analysis, translation, but also as you see, you can calculate embeddings, you can do LLM inference, you can do question answering, you can do vision transformers, right? You can do visual document, question answering, table understanding, speech to text, right? So basically there's quite a few things that are there. So that's Spark NLP. Overall, just as an open source library, now celebrating more than 7 years of releasing software every 2 weeks. And that's still the promise that we'll keep you at the state of the art. And then let's talk about where people use it specifically in the generative AI space. When the core aspect, the core design aspect within Spark NLP is the concept of a pipeline. Okay, and when you don't use the one-liners, when you want to combine models You build a pipeline. So you can come and say, oh, there's this PDF. I'm going to do some computer vision, do some table extraction. Then I'm going to split it, maybe do some sentence splitting. I'm going to do spell correction, and then I want to extract, I don't know, names, entities, normalize it. Okay, so you have different models that do it, and you put them in a pipeline. The interesting thing is that when you see the pipeline cluster, we actually use the Spark ML pipeline class, meaning that every Spark NLP pipeline is a Spark ML pipeline, which means that it is natively scalable. Okay, so all of this, when you call fit or you call transform, it can run on a cluster. Okay, so it means that first of all, this is its own code base, so this does not use Hugging Face or Spacey or anything in the background, it just cannot. All the algorithms are actually designed to run on a cluster at scale. Okay, so just implemented like that. There's no copying of data, which is partly would explain some of the speed and scalability benchmarks that you'll see. And the nice thing, if you want to run it on your entire S3 bucket, entire history, you can have one Spark ML pipeline where you can sometimes suggest, okay, read it distributed from, say, S3 or HDFS, okay, into a cluster, run it on the cluster, write it back to another cluster. Okay, you give it the whole pipeline to the Spark executor, it does the planning before you start, right? So there's no, we send everything to a certain machine and no API, you don't need to manage distribution. Really, you let Spark do the one thing it does well, which is really plan those execution pipelines. Okay, so in this sense, this is really kind of designed for scale from the ground up, right? You can load at scale, you can write at scale, you can use the execution planner to do just that. And the other thing we do a lot of optimization for speed, including a lot of what I'll talk about is on a single machine. So our goal is to get to a point where if you run something just on your laptop, it needs to be faster than anything else. Okay, because some use cases just don't require the scale, but even if you do, when you're at scale, you care a lot about cost and compute costs. Okay, so this is very important. So we have, actually we work with Intel engineers and NVIDIA engineers. We have separate builds for those three hardware platforms. So one big use case is calculating embeddings to populate a vector database. Okay, so every classic RAG LLM use case, we come say I have all of my internal, say, I don't know, SharePoint documents, financial disclosure, patient data. I want to be able to have an LLM that can search for them as context. Okay, so what I need to do, this is the classic vector database use case. I take the documents, I calculate from each document the embeddings, right? This is usually the costly side. So either document or usually each section, right? Because you need to break the documents correctly. You calculate the embedding for the section, you store it in the database. And when there is a query, so someone says, oh, I want, give me all the South Asian companies who have had a revenue growth of more than 50% in the past year, right? You want the LM to translate that query also into an embedding. You send it to the vector database. What the vector database does is find basically the semantically closest document, and you get that back. What we are focused on is the pipeline for calculating embeddings at scale. Because one place where you would need the scale and would have the compute issue is the fact you may have many documents that you need to actually load. Okay, and what you see here is a comparison also on a single machine between calculating embeddings of 10,000 documents, 50,000 documents, 100,000 documents. Each document is about like 1 page of text in this benchmark of Spark NLP 5 versus Hugging Face. Okay, so this is not a scale distributed thing. This is just single server. Okay, and you can see that on the original embeddings, it was 3.69 times faster, 3.85 times faster, 3.94 faster on the bigger data set. On the quantized embeddings, it was, the gap was even bigger, right? Because between 567 and 688 times faster than Hugging Face. Okay, so whether this is your actual latency to process something, or whether you're actually paying for compute, right? Because if you're paying by CPU minute, by CPU hour, this is the actual costs, right? If you have 10 million documents, are you going to have to pay, for something to run for a week, right, or something to run for 3 hours? The second thing to note, and by the way, everything I'm showing you, of course, the notebooks, the code is public, right? So you can reproduce those benchmarks yourself, and you can, we can send you links to where the code is. The other nice thing is without any code changes, right? Because at the end, underneath those one-liners, there are Spark pipelines. You can just scale, you can just give it more workers, and it uses those workers, which is something that if you just use, for example, transformers, sentence transformers, LangChain out of the box, it just doesn't. So as you can see here, 50,000 documents, 100,000, 1 million documents. You do not change the code at all. You can see here's the Databricks machines we used. And you can see just the runtime going down, right? So you just go into Databricks, you said, look, just add more workers and do that. And you can see it's near linear scaling at those ranges. Okay, so really, you just give it more machines. You give it 10x more machines, it runs into 1/10 the time. And for example, if you're on a platform like Databricks or any cloud providers, what it really means, it runs at 1/10 the time at the same compute costs, right? Because we're paying by CPU minute. So here's, for example, one of the things we do here, we do a lot of work in healthcare, is to do embeddings and transform all of PubMed, right? So all of the medical research, it's tens of millions of documents, right? Everything that's public research. And here you see for media, 1 million record, we get it down from 43 hours to 3 minutes. Okay, and that's without any code changes, right? So those are the kind of things you should expect. Here's another example, a comparison, and you can see how the code looks like. In Spark NLP, first of all, it's just another step in a pipeline. You can come and say you can load, in this case, right, MPN embeddings, right, but there are different embedding architectures, different code base, and just another step in the pipeline. And usually, your pipeline would be more complex than that. You not just load the document and process, you load the document, you split it, you encode it, you correct the grammar, you change the spec, you normalize the dates, and then you do embedding. So it's all still one pipeline you load into memory once. And then you can see how it works with, in this case, set transformers on HayStack with Ray. And also, this is single server, just single machine, low scale. You can see, look, like this is 10 documents, 50 documents, 100, 150, and 200 documents. You can see the speed up. So here it's number of seconds, so lower is better. Okay, so you can see with Spark NLP, basically you have some setup to load the models. There's a very low overhead to get the additional document done. Okay, which is important to say, even if you just have 200 documents, it's going to be the difference between 30 seconds and 170 seconds, which is important. And of course, the other thing is scaling, right? So this is really, this is still a single machine, same data set, same small data set, just adding more workers. Okay, if you don't want to wait for 3 minutes, fine, we can make it 6, 7 seconds. Okay, just actually use the CPU cores that are there without changing any code. So that's one use case. And what we are seeing is a lot of people, you use LangChain, use sentence transforms, use whatever you need. When people get above usually 10,000, 20,000 documents, and really they see those things really just starting in hours and days, they move to this, and then yes, you can easily go into the millions or tens of millions of documents that are there. So that's one thing. The second use case is, what if you just want to use an LLM? Okay, so in Spark NLP, you have all of the NLP things. It can do translation, it can do, it can extract dates, it can extract many different kinds of entities, it can do sentiment. But look, I just want to do the prompting thing, where I give you a prompt, you want the LLM, and you give me a result. Okay? Sometimes you just want an API endpoint is actually convenient. But what if you do want to do this at batch? For example, here are 5 million documents. I want you to translate all of them to English or to Portuguese. Okay, I want to simplify them. Okay, people do this with legislation. Here is early 20th century forms and legislation. You can just translate them to current language. Summarization is a very, very common use case, right? So I want to summarize things, but can you just do it? But basically, I want to have an LLM. So the nice thing is that calling an LLM for inference is really just another step in the pipeline. Okay, so you can come and say, okay, this is, for example, run speech to text, then do some spell correction on it, then identify the speakers, then for this speaker, translate this to Spanish. Okay, the translation to Spanish is an LLM. Or for example, summarize which of our products are they asking about, right? Or where should this support request go next, right? Which is a classic, you just want to do it with prompting. So this is just something you can do, and there are several LLMs that are there. So also, what you should expect to have really all the major LLM, like, Llama 2 and 3, Pi 2 and 3, quite a few others. I just released this week with a whole list of new supported architecture. And same thing, we curate all the major models, and they're available to you with one line. We look at speed, and we look at scale. And the reason we look at speed is mostly cost. Okay, LLMs can become extremely expensive to run at scale, and this is intended to help with that. So what we do here, this is we start with a super small data set, like 59 kilobyte, that's the whole thing, just to show this is effective at small scale, right? It's a summarization. So you have a news article and the prompt is please summarize it. Okay, and this is really a classic thing. You give it a whole bunch of documents, can you summarize all these documents for me? And what you see here is a comparison between Spark NLP and just running, just Hugging Face on Spark, right? And this is just Llama 2 models, okay? And this is really something you just try for yourself. There is a big difference in the overheads in loading those models, running them, really just doing the basic inference. If you're paying any cloud provider, right, for CPU, if you're paying for hosted endpoints, if you're hosting it yourself, as you can see, there's like a, it's like an 8x difference in terms of the latency, the time it takes, and same difference in terms of cost, the cost to you. Okay, so you can be much more efficient on running those things. This specifically benchmark is actually not on a GPU, for course, it's on a CPU. I want to just call a shout out to the Intel team. In the engineering team, they contributed code. The teams contributed open source, same as NVIDIA. They helped integrate OpenVINO into Spark NLP, which is, it's a library for Intel-specific hardware. The text models optimize them basically to use the most of the newest modern chips. And you can see on Llama, you can see the difference between using an Onyx model and using an OpenVINO model, right? Often you will basically take the Onyx model, optimize it for specific architecture, and you can see it's it's almost a 10x difference. It's also a difference in CPU utilization when your rank actually uses all of the CPU. So that's a really nice work by the Intel team here. In terms of costs, right, because this is often an issue. So what we use for this benchmark is a mid-range server on AWS. This costs you see, it's like just under $440 a month. Okay, so these are the costs to run those things. The models are completely open source, so this compute is your only cost. Okay, there's no other overhead, there's no other cost that you need to pay. You can say, this gives you a document in about 3.3 seconds per document. And of course, you can scale it, right? You can use, and the thing is, you don't need to buy necessarily the most expensive NVIDIA machines. You can scale horizontally here. Okay, so that's really, the good thing is that now you have a choice. Okay, you don't have to go with the A100. You can have a whole bunch of smaller machine. The cost is still much easier. And of course, you can scale up and down in terms of cost much easier. And really just one thing to note is there's a very big difference in really just the core implementation of how you run these models. Okay, so if you use, for example, LangChain and HayStack, right, on the kind of the default settings, which rely on sentence transformers, usually on Hugging Face, you're just paying an order of magnitude more to do exactly the same thing. Last thing I want to say is if you do like LangChain and HayStack, you can say, well, yeah, I don't use them for this, but like I want to use them for chain of thought reasoning. We do have also native integrations with them that are completely open source Apache 2.0, Apache 2 licensed, which means you can use your favorite libraries, just replace the actual LLM inference piece or the embeddings if you load RAG with those libraries and really just get that benefit. Okay, so all of that is available to you, completely free and open source. Quite a few people use it. If you need more, let us know. With that, I'd like to move to the third use case, which is showing really end-to-end RAG pipeline. So that's in case you don't want to use any other library, and you want to make sure that really within kind of the same library, the same architecture, the same benefits of speed, you can do the entire work. And Vaisal, Johnson Labs, head of data science, will present that part.
Thank you, David. Hello, everyone. So David already covered the intro to Spark NLP and what is the advantage of using it over other libraries or technologies. So I'm going to go over into a bit details about RAG architecture and how you can build the same within the Spark NLP using license and open source components as well. As you know, classic RAG architecture has two main components, right? Indexing and then retrieval. Retrieval also includes the generation part as well. So you basically index your document and then vectorize them and then write into a vector DB. When you ask a question, you get the embeddings of the question and then find the most similar simplest, and then LLM does its job to do the like synthesizing the entire information into one coherent answer, right? So that's this usual step. And there are many tools out there already that people use for the document loading. You can use like LangChain, HayStack. They have PDF loader. They have a CSV loader. You can for the document splitting. Most of the people goes by only with some default splitting strategies, which is the most important part, and then I'm going to touch that a bit later. So the sentence embeddings, you can use Spark NLP, you can use Hugging Face, you can use many other libraries to load all these embeddings over there. And then the last part is vector databases. They are more or less same depending on the use case, but there are many open source as well as a licensed solution over there. So these are the tech stack that you can build any RAG architecture, and there are many other combinations that you can do with this. So how you can do this within the Spark NLP if you are already using LangChain, HayStack, etc., right? We have a native integration, as we mentioned before, that it's a little bit covered at the bottom, but right now it's one-liner code that you can just collect embeddings within Spark NLP without ruining your LangChain or HayStack pipeline, which means that you just replace the embeddings collection part with Spark NLP part so that you can delegate the most expensive part to the cluster and then collect them back and then write into a vector DB without ruining your pipeline. So it could still be LangChain, HayStack. And so this is like the embeddings that you see on the left-hand side, every day it's changing. There is an MTEB leaderboard, as you know, which is a sentence embeddings leaderboard at Hugging Face. So people still sadly use like OpenAI embeddings most of the time, but there are better solutions like 3 times, 4 times better embedding solution out there, which is open source that you can also use. And then, as you see, the scaling factor, so it is like 3 seconds versus 43 seconds when it comes to 1 million documents to collect the embeddings with classic Hugging Face versus Spark NLP library. So, which means that you can get a better accuracy and faster response if you use your local embeddings by using this library. Let's do RAG from scratch using only Spark NLP without using any LangChain or HayStack, right? So indexing part, the first component. As you see, everything starts with loading the documents, but the next step, you need to right now split the documents into different pieces so that this will be your meaningful chunks at the end of the vector DB when you need it. So for the splitting the document, I have a dedicated slide for that part, by the way, but just splitting, there are many options that you can do within the library, like you can split by char, token, sentence-wise, NER-wise, keyword-wise, which is new, by the way, which means that if you want to just split the documents, not by char or words, but you split by sections, right? I want to split my document into sections so that because if you have a corrupted input in the vector DB, the LLM will not see the context. So we also do back and forth to be able to find the preceding and the following paragraphs, by the way, like a split as well. Anyway, we have many options. The next stage is embedding stage. Any embeddings that you see in Hugging Face, like OLMPNet, E5, GTE, BGE, you can use all of them. So the next stage is like embeddings collection. You can pick any embeddings that you have seen in the Hugging Face hub or from our hub, which supports Onyx and OpenMinO format as well. Or you can use your own fine-tuned models, which we already use in our licensed healthcare library as well. And then the last stage is vector DB approach. This is the first vector DB implementation running in a Spark cluster, and then you can stitch your metadata as well over there, and then start querying this, which means that without breaking your pipeline, because if you use LangChain or HayStack, even if you collect the embeddings within Spark NLP, you need to collect them, you need to get out of them from the cluster and then write into a vector DB, which is not a Spark cluster anymore. So in the vector DB approach, right now you can do this without breaking your pipeline. You can just let it run over millions of documents. And we are using the same techniques that the other open source vector DB engines are using, like HNSW, right? And then it also allows metadata filtering way easier than others. Of course, you may want to stick to your own Elastic cluster, which is also possible, like Elasticsearch. So you can just replace that vector DB with Elasticsearch vector DB, and then you can still use the same pipeline on the left-hand side, right? You split your document, collect the embeddings. Now you can just stream into an Elasticsearch without ruining your own pipeline or your own tech stack, which may be a little bit like non-trivial because of the querying by metadata, but we have a wrapper for Elasticsearch as well coming up in a month that it will be much easier to query Elasticsearch as well. So the next part is retrieval part, right? Now we have the vector DB. We wrote everything into a vector DB. Now we need to load that vector DB and then pull the most similar snippets according to my query and plus by some metadata. Like give me all the publications from PubMed published later than 2015, but earlier than 2018, let's say, and then it should be like the impact factor should be XYZ, etc. You can even do all this and then pull your splits rather than just the most similar one, but the one that fits your into criteria. But another most important thing is post-processing, because there is a huge difference between just pulling the top K split versus post-processing like a diversity ranker. Because when you pull the first most similar splits to your query, they are all similar to each other as well, right? So you need to diversify this a bit by using some ranking, so that you need to have more distance between the splits, even if they are close to the query, right? Oh, another one is lost in the middle, right? Because if you have 10 documents, the ones that you append each other and then send to LLM, right, for the final answer. But the ones that are in the middle are usually get lost within the context. So that's why there's a lost in the middle ranker that is like shuffling. Like rather than 1, 2, 3, 4, you do 1, 2, 3, 4, so that you put the most important and most useful content to the both ends, so that LLM doesn't get lost on the most important context. So now this is what you get when you query this DB, which means that you query with all this metadata on the left-hand side, and then that is what you get given your query on the right-hand side, with all the information, similarity scores, distance, publication date, etc. So that you can right now stitch them together and then send LLM for one single answer, right? So, and then you can also store them somewhere and then do a bunch of other stuff. The most important part, right, is the document splitting. So LLM's role over there is not that important. Like according to my idea, let's say, LLM's role can be reduced in a RAG architecture that into as small as 3 billion models. You don't need to boil the ocean just to synthesize the splits. Of course, the hallucination, because the larger the model, the hallucination also higher as well. Because LLM's job over there only synthesize the top K splits that is returned by vector DB. Of course, sometimes it tends to hallucinate further. Why? Because if the question is very easy for LLM to answer, it just skips the splits and then try to answer something. Well, that's why we do some LLM fine-tuning as well, reduce the size of the model, fine-tune with the context, so that you don't need 70 billion model just for RAG, right? So then, coming a few steps back, document splitting. Why? Because document splitting is usually skipped. They just load it. People just tend to load it. And then there are many novelties happening in the other stages. But the document splitting is the more underappreciated area right now that we try to focus, because we mostly work with the healthcare companies and then deal with the healthcare data, which is messy. But we saw over there that if you just plainly split into charts or tokens, it will never work. So you cannot even find the relationship between across documents. So that's why you can customize document splitting by using classic NLP. This is also grounding, by the way. So if you just split and then attach all this metadata by using classic NLP techniques like extract entities, titles, extract key information. Maybe you have a patient note, you extract ICD-10 code, RX norm code, and then attach them as a metadata. Then you can categorize your inputs as well. For example, give me all the patients who have a heart failure. Maybe that term is not happening within the document, but if you have the ICD-10 code, you can find the parent category and then attach it into the split. So you can apply many other techniques to augment your split. You can even summarize your split and then index them as well, right? For example, you can detect all the section headers by NER models, name identity recognition models, and then use document splitter with this header list, so that your document is splitted into the headers within the coordinates of all these headers, right? Since we are running out of time, I'm trying to cover as much as I can. So you can use all these techniques that we have. We have more than 2,000 pre-trained models in healthcare NLP library, by the way, that you can use all these techniques to augment your one-liner, by the way. Everything that you see in your sequence can be collected in one-liner pipeline, pre-trained pipeline, that you can attach all this information back into your chunks, like a document splits, so that when you query, you can use this as a metadata filtering, right? For example, you can keep adding new metadata to your splits. This is the difference between, like, it is without augmentation. Let's say that you have a drug leaflet. If you just split your drug leaflet and then try to find the adverse semantic, if you don't append the drug name or the section to the corresponding splits, the LLM will never see this because LLM doesn't jump between the splits, right? LLM only deals with the splits it gets from vector DB. But if you put this information in the metadata after splitting and then show LLM these splits, it's going to focus more on, it's going to differentiate the useless splits from the useful ones. So, like this is a default split that majority of the people already doing with LangStack, like LangChain, HayStack, etc. But default splitting doesn't observe section boundaries, headers. Ideally, each split should belong to one section, depending on the document type. If it's PubMed, it's better. If it is clinical note, maybe you need more information rather than just section-based splitting. Like another important thing, if you have tables and charts in your documents, how are you going to vectorize them, right? You cannot just use the same vectorization if it's visual content, right? What we do is that we do chart to text or table to text as well. Not we actually, you can also use any other table to text or chart to text and then index your content in your vector DB so that you can, when you ask a question regarding this chart, when you index that, the definition, like run a pipeline to extract this definition and then write into a vector DB, it will be able to show the chart after the question, right? So we covered many augmentation techniques for the splits, but I will just try to cover what would happen if we haven't done this, right? I'm not talking about the split. I'm talking about the RAG accuracy, final accuracy right now. If you don't do split augmentation, if you don't do, observe the key differences between the context while splitting, just randomly split, the differences between blue and green, by the way, like a red and green as well. So we did this for the PubMed articles, used all MPNet embeddings, and then if you just go by the default splitting, the accuracy is final faithfulness, like a faithfulness to the source document is 73% to 87%, which means that you can have more than 15%, 14% jump just by observing all these differences that I just tried to cover. Everything can be reproducible. Here are the notebooks that you can go ahead and we have several webinars, which I already covered this, how to augment your splits, how to use LangChain with Spark NLP or without Spark NLP on LangChain or the other way around. We also have how to build your agent by using all these models. Maybe you want to talk to LLM and say that anonymize this text. So rather than trusting LLM to do this, it can go ahead and then pull the corresponding the identification model coming from Spark NLP library and then anonymize this and then send back. So LLM's role should be reduced as much as possible over there. Thank you.